Did you know you can make some really weird batteries? I mean, we all seen the middle school projects making batteries out of lemons and potatoes, but how do they actually work? And what else can we use to make power? Well, I went down a rabbit hole trying to make some out of soda, and well, this is what I learned. So, before we get into the fun stuff, we have to go over what is a battery, why does this work, and what's happening here. So, a battery is a type of spontaneous reaction that occurs. Spontaneous reaction is a reaction that will occur naturally on its own. You can think of it like rust. No one is going and creating rust that naturally occurs on your bike outside in the garage. You're not making that happen. It's just naturally occurring. Versus something that is like a chemical heat pad that you have to break manually. You are putting the force in, it's an external force, it is non spontaneous. Another fun way to think about it is if you are making a really strong drink, you are a that is a non-spontaneous drink because it is super strong, but you made it super strong versus say a wine or a whiskey that's been aged a really long time and has a really high alcohol content due to this. That is a spontaneous drink. So, a battery is a type of spontaneous process. So now we know that it's a spontaneous reaction. But why does a spontaneous reaction create electricity? Well, if we would refer to the lovely whiteboard I have. All right, so this is kind of what we're going to be making today, but this is a galvanized cell. A galvanized cell is what we consider to be a battery. We have a half cell here and a half cell here, and this is an electrode as well as this. This is the anode. An anode does oxidization. Oxidization means that they are losing the electrons. And this electron is going to be traveling from the zinc up and through. The voltmeter counts how many electrons are passing through, and then we're going to continue down into this copper. And since it's reduction, it's going to gain electrons. The salt bridge here is to initialize movement back across so that they can return and you have a full cycle, excuse me, so that they can return and then you have a full cycle. I will not be utilizing a salt bridge today in my experiment. This experiment's made for kids mostly. I've only seen a couple of college uses, and it's usually teachers asking what is going on and having students explain. This is meant to be a short term demonstration. It's not meant to be a long term solution. I'm sorry, you're probably not going to be charging your batteries in the zombie apocalypse with some soda. But these three reactions up here are called cell notations. The cell notations go from the anode to the cathode. I color coded them as best as I could. And these are going to be the three reactions that we're playing around with today. We have a zinc with phosphoric acid and copper and phosphoric acid. We have carbonic acid, the second row. And we have citric acid. This is going to be our name brand cola. This is going to be our just carbonated water. And this right here is going to be our citric acid. So a Sprite or some similar beverage. This right here, the voltage you see on the meter, that's our ideal voltage for copper and zinc. I could tell you right now, we will not reach that. It is purely because this is not an optimized setup. This is a setup just to demonstrate how electrons move, but we're going to try to make it as scientific as possible. And we are back from the whiteboard. All right, so As you see, that is the theory that we'll be playing around with. We have some phosphoric acid, some carbonic acid, and we also have citric acid. Those are the three acids we will be playing with today. They are pretty prevalent. We drink them all the time. And I wanted to see which one was the one causing this reaction, or at least the one that contributed the most. Or are they all equal? Who knows? Maybe we'll see in a few minutes. Well, you'll see in a few minutes. I had a while to go. But it was a super fun experiment to plan. I was able to isolate each using a soda streamer. I would carbonate it the same amount, and I would do it uncarbonated in the same syrup ratios and everything. It was a really, really fun experiment. I had a blast with this. I was inspired to do this because I couldn't find any literature on this specific reaction. I could find some like how-to guides for kids and for like teachers to do for like kids, and most of the time we're talking like middle school, maybe high school level kids. And the only time I ever seen this talked about on a collegiate level was two random forum posts, and it was students looking for help on their homework because their teacher did this demonstration in class and they could not figure out how it worked. And let me just tell you, same. That's why we're here. That's why we're doing this. I understand why, but why? Which acid is the one causing it? And I heard it all. Some people claim it's carbonic acid because of the bubbles forming on the metal and would cause more reaction. I heard it was phosphoric acid because it's the stronger acid. Same thing with the citric acid. It's a stronger acid than the carbonic acid, even though there's more carbonic acid, which means that there's more to react with. And it was a rabbit hole to go down. I went down it for a while. And that's why we're here. So anyways, I will stop holding you up and I will get on to the experiment and the result. But before that, let me tell you my little hypothesis. I think that it is most likely going to be carbonic acid just because it has the bubbles in it and it's going to agitate more and give it more surface area to cause a reaction. And honestly, that's my guess. But we'll see how close I am, see how close you are. Let's go. So you can see here, this is how I make the soda. I do 5 pumps on the soda stream, and then I will take and put in the recommended amount of syrup to get the ratio that is most similar to the sodas we buy at the store. It is a pretty simple process, and it's really easy for me to control each aspect of this experiment because it is the same amount of syrup no matter what test it is, and it's the same amount of carbonation no matter what test it is as well. This is my first control test. This is maxed out at 99.5. We used AC instead of DC on the settings on my voltmeter because the DC settings were just too low to see a discernible difference. So I chose to do it on the AC setting instead. So that's why the numbers we are seeing are these. These are still volts, it's just a little less. Here we have the first run of phosphoric acid by itself with no CO2. This ended up maxing out at 51.4. And now the second test for phosphoric acid with no CO2. This one maxed out at 53.8. Very similar numbers. It's about half of what our control was. Here we have just CO2, our first test. This ended up maxing out at 36.4, which is a lot lower than I expected it to be, honestly. And here is our second test for CO2 only. This one maxed out at 78.0, which is pretty high. I was pretty astonished by this. I think it's something to do with the bubbles interacting with the metal. And here we have starry or citric acid by itself. This one ended up maxing out at 64.5, which is a lot better than the phosphoric acid. And here is our final run for the tests. The last starry with no CO2 added into it. This one ended up maxing out at 56.3. Again, really good. I'm very surprised how good citric acid ended up being overall. And here we have some data that's nicely organized and pretty looking. But overall, the control was, of course, the highest. It's a combination of multiple acids. Makes sense that it is the one that has the most reactivity with the metal. We had the CO2 tests, which were very widely based. We had one CO2 test that was pretty low and another that was super high. I think it's something to do with how the bubbles were interacting with the metal and how many were popping on it versus just staying on it. The phosphoric acid was pretty even, and same thing with the citric acid. The citric acid did beat out the phosphoric acid. So if you are going to do this with some kiddos, I would probably recommend using some Sprite instead of some cola because the citric acid does seem to produce a little bit more of a reaction overall. And yeah, those are the results from the test. Like I stated before, I think the CO2 had the largest variation because there's the variable of the bubbles. The bubbles could form more on the metal and pop at various times, leading to some being higher than others, kind of like a physical reaction versus a chemical reaction. I could relate it to the soda Mentos. Soda and Mentos, if you don't know, if you put Mentos in a soda, it will explode. Well, this is actually a physical reaction because the Mentos has nuclei points on the Mentos that will attract the carbonation, the CO2, and will create that gusher that we all know and love. And that's because of a physical reaction with it. If you use the fruit Mentos, it won't work because there's a wax covering and there's no little bumps and for the CO2 to cling to and be released off of. So I think that's pretty similar to what we're seeing happening in this test. Um, I don't know how I could possibly change this to work better, but if I did in the future, I'd probably run a few more tests. I only did 2 of each just for time's sake. It took me about an hour and a half to run all of those tests. Um, I would probably want to run more. It was really fun, honestly. The phosphoric acid, we did see it was pretty even between the 2 tests, which was great to see. And that's why, again, and the same thing with the citric acid, they're pretty even between the two. So that's why I think it is a physical aspect of the CO2 that is causing such a large discrepancy to occur. The phosphoric and the citric acid, though, were pretty even. And as we see, the citric acid beat phosphoric acid out a little bit. But overall, I would probably say it's pretty even between the acids on which is causing this reaction. And as the control was double of any of the ones we got alone, besides for the one outlying carbonic acid test, I would say it's a pretty good bet that it's a pretty equal reaction between either carbonic acid or the phosphoric or citric acid, whichever is present in the soda that we are using, which is cool. I got the answer that I was searching for. It's pretty even. It's all pretty pretty dead on even, which is really cool to see. I did not expect that. I expected one to blow one out of the water, but it didn't. And yeah, I think that's cool. But it was a lot of fun to run. and I'm very proud of my results. It was very fun to see the theory be put into use, and I love being able to make this. I love setting up the anodes and the cathodes and being able to visualize electrons running through with the voltmeter. It was a lot of fun. I'm very happy with the results overall. And yeah, they were pretty equal overall. This experiment did not go how I thought it was going to go. I thought there'd be one that I could tell you definitively this is the acid that is causing the reaction to occur. And that was just not the case. It wasn't a majority of, oh, carbonic acid is the one causing, or phosphoric or citric acid. It was truly a combination of all of them that would create this reaction to occur. And I completely see why this is a kid's experiment. It was a lot of fun to complete, and it made it really easy to visualize the aspects of electrochemistry in a pretty simplified way. You were able to see the anode, the cathode, you were able to say, okay, this is the electrons traveling through. It made it so much easier to visualize than just looking at diagrams on a computer or in a book, which is always fun to see. And yeah, I had some problems in the beginning with this experiment, just trying to get it to work. I ended up having to sandpaper the metals and doing some other creative solutions. And that's also why I used the setting I did on the voltmeter, because that's the only one I could get to work. But overall, I think it was a pretty successful experiment that showed that at the end of the day, it's a pretty equal reaction. And yeah, that's what I got.